Hello, thank you all for joining this event. For those who don't know me, my name's Ross. I run this Java Talks Meetup and work for Preactive Talent Solutions here in Sydney. We partner with some of the leading tech companies in Australia to help them hire the talent in the market. As part of this service, I've worked with Atlassian on site in their talent team for the past 2 years, helping them scale their engineering teams here in Sydney. I've been lucky enough to host this event, so a special thanks to Ali Pavani and Simon Waite for introducing me to Ksenia at GridGain Systems. I'm really excited to introduce our two speakers. We have Simon Ritter, who's joining us from England in the UK. Simon works for Azul Systems and is currently their Deputy CTO. And a special thanks as well to Denis Magda. It's currently 1 a.m. where he is, maybe a little bit after that now, in San Francisco. He's the VP of Developer Relations at GridGain Systems, and he's joining us on a really awkward time zone, so thank you very much. The guys are going to be covering how to minimize the influence of garbage collection pauses and scale to petabytes. If you've got any questions throughout the talks, please just pop them in the chat section, and at the end we'll do a Q&A. So handing over now to our first speaker, Simon, for his first talk.
Thanks. Okay, thank you very much, Ross. Yes, so my name is Simon Ritter, and I've been working with Java for quite a while now, having joined Sun Microsystems back in 1996, and then followed Java all the way through that. Got acquired by Oracle, spent 5 years there, and then for the last 4.5 years, I've been at Azul Systems. Denis, I don't know if you want to say a couple of words of introduction.
I can also say that my whole professional career started with Java. As Simon, I had an opportunity to work for Sun Microsystems. Then I joined Oracle Java engineering group. So two of us, we have pretty solid experience in Java. And today we want to talk about how to take Java-based solution and start building low latency systems using only Java-powered software stack.
Okay, so first thing here is it's got a little example of how latency can be very important, and reducing latency can be equally as important. And so the example here is about Southwest Airlines. And back in 1972, Southwest Airlines was a very small airline, only had 4 airplanes. And because of the way that things were going for them, they needed to raise some money. And the only way they could do that was by selling one of their airplanes. So they did that, leaving them with 3 airplanes rather than 4. Now, normally you would expect them to have cut routes that they did because they wouldn't have enough aircraft to service those routes. But what they actually did was they figured out that by reducing the latency of the turnaround time they had at the airports, they could actually do the same number of routes with 1 less aircraft. So they actually managed to reduce the turnaround time down to 10 minutes. So literally pulling up at the gate, 10 minutes to get everybody off, all the luggage off, all the luggage on, all the people on, and off they went again. Now, since then, obviously things have changed a little bit, but they're still one of the fastest airlines in the world in terms of their turnaround time. And so that's a good example of how reducing latency can actually have a huge impact on terms of like the costs of your systems and so on. So Denis, would you like to say a bit about this slide?
Yeah, absolutely. And to give you folks an example of how of low latency systems of our domain of software development, we can talk about these 3. The first one is payments processing. Probably that's one of the most frequent operations we as humans kind of go through daily. We swipe credit cards, and then behind the scenes, there are many backend systems that have execute a multi-step process that ensures that your transaction is not fraudulent, that we need to take and kind of commit this transaction. We need to debit one account, we need to credit another account. And usually most of those steps throughout this transaction payment process need to be completed within the boundary of 20 or like 200 milliseconds, depending on your bank. The other example from the same low latency realm is 5G-based infrastructures. Right now, the world is moving towards this new ecosystem. And if you take a look at specifications of 5G-based solutions, most of the operations, like whenever you are going to analyze your traffic, whenever you're going to do some operations, most of those operations, again, have to complete in like 5 milliseconds. And the most extreme use case is electronic trading. We can see all the market ticks in real time, and all those backend systems need to process all those fluctuations and changes with the prices within the boundaries of nanoseconds. And the question we want to ask in here, like, does Java have any component that can kind of affect the latency of our systems? And that's kind of the overall topic of our discussion.
Yes. So as we were saying, basically, the issue that we often face is the idea of garbage collection and how that makes the whole predictability of the system that you're using much less predictable. So that's one of the big things that we're going to talk about for the rest of the presentation. So yeah, in terms of like requirements for this, obviously the first thing we need is predictable and consistent latencies. So in some way, we have to make the garbage collection unnoticeable. And that's the part I'm going to talk about in the next few slides. Denis, did you want to talk about the other parts?
Yeah, absolutely. And the other two requirements here is that section will be introduced during my part of the presentation. And the second requirement is low latency and high performance. Absolutely, you can always build a pretty powerful system, but also right now there are a lot of technologies that are designed to keep your data in memory. And as we will see, if you can read and serve all your records from memory, you can get the lowest latencies possible. Just because, you know, memory, DRAM is much closer to CPUs than your flash drives. And the other thing is that usually we are building the systems sometimes for the needs of today, but let's say in a month or in a year, kind of the requirements can be changed. And instead of, you know, processing like thousands of requests, your system should be capable of dealing with an increased number, like dozens of thousands of operations, which means that it would be ideal if the system is capable of scaling horizontally. And here is we are talking about, let's say, new instances for your application services, as well as kind of horizontal scalability for your backend system. And going forward, what we are going to check, we are going to introduce you this kind of solution. Simon, could you please move to the next slide? Yep. So generally speaking, that's probably not the only one solution that you can build to kind of have a Java-based stack for low latency scenarios. But anyway, that's something that we designed. That's what we are using, and that's what we confirmed is fully workable and can sustain low latency boundaries. So here is we are going to have a distributed in-memory cluster. So because memory can serve all our records in the fastest way possible, that cluster will be horizontally scalable. That will be Apache Ignite cluster. Probably some of you are already aware about that in-memory computing platform. If not, it's not a big deal. We are here to introduce you to it today. And also, Apache Ignite, by definition, is also a Java middleware. It's a distributed in-memory computing platform, but it runs in Java. And to make it possible to use Ignite for low latency use cases, we need a virtual machine, Java virtual machine, that can eliminate significant Java garbage collection pauses and have more sophisticated optimizations and features inside. That's why we will be talking about Azul. That is a virtual machine that powers our distributed in-memory cluster as well as our Java-based applications. So Simon, let's move on and
okay, right, great. Yes, so let's talk about what Azul do with Zing and the idea of Java without the pauses. And if we think about what actually happens with Java, what we're dealing with here is a managed runtime environment. Essentially, your application is sitting on top of the JVM, which then sits on top of the operating system. So it introduces this intermediate layer between the application and the operating system underneath. And that's very good because obviously the JVM can take care of a lot of hard work, which normally detracts from developers and being able to be efficient and so on. So things like the fact that we have a managed runtime for memory. So we have the garbage collector that deals with collecting unused objects so that we can reclaim the space and we don't have to worry about freeing those explicitly. The problem with the garbage collector, as we've already said in the earlier part of the presentation, is this is inherently non-deterministic. We can't predict when the garbage collector is going to run. It depends on so many factors: how frequently we allocate objects, how frequently we stop using those objects, how much memory space we have, how much fragmentation there is, how objects get moved around within the heap, and so on. So there's lots of different things that basically make it impossible to predict when we're going to run the garbage collector. And the other thing that's a very big consideration in terms of the collector is the fact that the pause times can be quite large. And the reason for this is that if you look at most algorithms that do garbage collection, they pause the application threads in order to do the garbage collection work and be able to do it safely. So they're going to move objects around within the heap. They don't want the application threads still manipulating those objects whilst they're being moved. So to do it safely, they pause the application threads, do the work, and then carry on. But that introduces pause times, as we're aware of. And as I say, those pause times can be very big. I mean, they could be the order of a few milliseconds. They could be, if you're unlucky, they could be seconds, maybe a couple of minutes even. Largest garbage collection pause I ever heard of was 1.5 days, which is a very extreme garbage collection pause. But apparently the company that was doing that were fine with that. And then we presented Zing to them and they were like, wow, that's incredible. Anyway, moving on. The other thing that we have with the managed runtime environment is the fact that we use bytecodes, not machine code. So bytecodes are the instructions for our virtual machine. And then obviously we have to take those and convert them into the relative instructions for the machine we're running on. And that's the whole idea of write once, run anywhere. So we take the same set of bytecodes, and regardless of whether it's running on Intel, whether it's running on Windows, Linux, ARM, whatever, we convert those at the time that we need them. And what this leads to is a warm-up time associated with our application. So we start off quite slowly, and then the performance gradually increases as we compile the code that we need into native instructions. So what we've done is to create the Zing JVM. Now, what we did was we looked at the issues that we had with performance on the JVM, and we said, okay, how can we improve that? And rather than starting from the beginning and simply saying, okay, let's completely rewrite the JDK and the JVM, what we said was, okay, there are some things that need to be changed, but not everything. So we took the open JDK source code and used that as our starting point. We make changes to that, but then to be sure that we don't break anything, we run all of the Java SE TCK tests. That's about 150,000 tests which are required to conform to the Java SE specification. And we make sure that we pass all of those. What this means is we have a drop-in replacement for other JVMs, and it means that you can be confident that because we are functionally equivalent to the other JVMs, your application will run in exactly the same way. So it will do exactly what you expect it to do. It will just perform slightly differently. From the point of view of what we change, the first thing we did was to remove all the garbage collectors in hotspot. So that's the serial collector, parallel collector, and so on. And we replaced it with a single one called C4. And I'm going to explain more about what that does in a moment. One of the key things about this is it is only supported on Linux. Now, technically, there's no reason we couldn't support it on Windows, but we only support it on Linux because of market demand and the engineering involved. And the reason for that is that we also have some things that work at a lower level. So initially, we had what were called the Zing system tools, which was in essence a replacement for the virtual memory system in the Linux kernel, so that we could handle the virtual memory mapping between physical pages and the address space in the JVM in a more efficient way, tailored specifically to the way that the JVM works. Now, because with the move to containers and the use of Docker and things like that, what we found is that people don't really want to be messing around with the host operating system underneath. So we now have a version of Zing which runs without the need for the Zing system tools, and we can use some of the more modern Linux system calls, and therefore it is just a direct replacement. You don't have to install anything else. You can deploy your Zing into your container with your application, your service, and off you go. The second thing we did was to look at how we could improve the performance of the code that's generated by the JVM. And that led to a replacement for the C2 JIT compiler called Falcon. And again, I'll briefly talk about that towards the end of my part of the presentation. And then the third thing we've done is to add some technology to the JDK, which allows us to eliminate as far as possible this warm-up time that happens because we're going through the phases of interpreting bytecodes, then compiling them using the C1 JIT compiler, then recompiling with the C2 JIT compiler, and doing that every time. So I'll talk a little bit more about that later on as well. Okay, so we have this collector called C4, and that stands for the Continuous Concurrent Compacting Collector. And that essentially tells you exactly what it does. So it's a continuous collector. It runs all the time in the background, figuring out when it needs to do some work. It is fully concurrent, meaning that your application threads can run at the same time as the garbage collector is doing its work. In addition to that, it is a compacting collector, meaning that we do move objects around to eliminate fragmentation and to keep all the used objects contiguous in the heap space that we have. So the fact that we can do this concurrently and compacting is the really tricky bit. And so I'll explain how we do that. So the first thing in terms of the basics of C4, it is using similar kind of characteristics from an algorithm point of view to other algorithms. So it is a generational collector, meaning that we divide the heap into two regions, young and old. The idea behind that is that most of the objects that you're going to allocate in your application are only used for a very, very short space of time. So if we can reclaim that space in the young generation without having promoted them to the old generation, it means we make more efficient use of the space and more efficient use of the garbage collector's time. So that's the reason that we have both young and old. We use the same algorithm on both. So we don't have different algorithms like you do in hotspot. We use the same algorithm, two regions, but it's still more efficient for us to do that. Most important thing about C4, it doesn't have a stop the world compacting fallback situation in terms of how it works. That means that at no point will we reach a situation where we say, oh, okay, we have to stop all your application threads. We have to do a full compacting collection on the old generation and make sure we've got all the space back. That just will not happen. All the other algorithms that you use, typically G1, CMS, and so on, will all at some point give up and have to do that full compacting collection. And that's what causes very long pauses in GC. In terms of the algorithm we use, it's three phases: mark, relocate, and remap. And again, very important thing about this is that all those phases can be done in parallel, meaning we can make it as efficient as possible by using multiple threads to do the work. Now, the key thing in terms of how we make this work in being able to do it concurrently and move objects around is what's called the loaded value barrier. And essentially, this is a read barrier, meaning that we intercept every reference that you make to an object when your application code is running. By doing that, we can actually enforce two rules, because what we do is we use the object header and we use certain bits within that to indicate what phase of the garbage collection we're in and also what state the object is relative to the garbage collector. Two rules that we can enforce with that are that we can ensure that when you get a reference to an object, if we're in the marking phase, it will always be marked as live data. So there's no danger of it accidentally being garbage collected even though you're using it. So it's always going to be marked. The second thing is that if we're in the relocation and remapping phases, then the object location that you get will always be the correct one. So you can make any changes you want to the object and they will not be lost because we're in the process of moving the object around. This allows us to do full concurrent marking and relocation with our algorithm. Many people often say, well, hang on, if you're intercepting every object reference, doesn't that mean that you're going to degrade performance by placing an overhead on the fact that you're doing all this extra work? And the answer is sort of yes and no. The answer is yes, because what we're doing is we're looking at these bits and we're essentially doing two instructions, which is test and jump. Test the bits, decide if we have to do some work, and if we do, we jump to a handler. Most of the time, we're not going to have to do that, so we just move on. So the impact, if we're not having to do any extra work, is only two instructions, which at the sort of hardware processor level is a single micro operation, meaning it's less than 1 nanosecond of overhead. So even if you're doing lots of object allocations and object references, this will not place a load on the system that you would notice. So as soon as you get to L2 cache, L3 cache, or main memory, the effect of those read times is going to be far longer than the impact of having to do the extra work of our load value barrier. How does this work? Well, when we need to do marking, what we do is we take the same basic approach as other algorithms in that we create a root set. And the root set is a list of all the objects that are accessible directly from your application code. We scan the stack, we look at the registers, we look at static variables, and we build up a list from that. Obviously, many of those objects are going to reference other objects and so on, so we have to trace all of the links from the root set to the other live data. So our garbage collection threads will gradually work through that, marking each object, tracing the links, marking all of those, setting the bits so that we know that those objects are still in use. Because the root set is independent data, we can actually do that in parallel. So there's no issue with being able to do that in parallel. What we also see is that the application threads are running at the same time. So we might get a situation where an application thread goes to an object reference and it hasn't been marked. So what we do at that point is we do our test and jump. So we say, oh, hang on, that bit isn't set. So we jump to the handler, and that will then set the bit in the object to indicate that it's still in use. So in effect, what we're doing is doing a very small amount of the garbage collection work in the context of the application thread. What we then need to do is obviously trace references from that object, but we don't want to do that in the application thread context because it could be an unbounded task in terms of how much time it would take. So to get around that, we simply pass the object reference to the garbage collector and say, okay, you deal with the rest of the links. Whenever the application thread references another object, obviously it will be marked. So that guarantees that every object you get a reference to is marked. What we then need to do is relocate our objects within the heap. So this is to compact them, to eliminate fragmentation. In the example I've got here, we've got 5 objects, A, B, C, D, E, and in order to relocate those, it's very simple. We calculate a new position for each object so that they're contiguous in memory, A prime, B prime, and so on. We can copy those objects, and we can do that whilst your application code is running. We will put a lock around the individual copy, but because most objects are very small, the time it will take to do that copy will be very small, so the time that you'll be blocked because of that lock is going to be very small as well. What we also do is we create a side table, and the side table lists all of the new positions of the objects that we've been copying, so that when we come to the remapping phase, we then have our garbage collection threads work through that side table, looking at the changes in reference, and it will then go to each of the object headers and say, okay, A has moved to A prime, so it will update the reference to the correct place in the heap, and it will set the bit to indicate that that update has been made. And obviously we can do that in parallel as well. We can have multiple threads running on that. The application threads are still running, and so again, we may get a situation where we go to an object and the object hasn't been updated. So the bit has not been set to indicate that the update has been made. So at that point, we'll jump to our handler again, and this time we'll change the reference using the side table to update the position of where the object is really in heap space and set the bit so that we don't have to do that again. Pass that back to the application, and the application has the correct place for the object reference, and so we're then able to make changes to that without any danger of corrupting our data. What this leads to is what we call the pause-less collector. Not totally pauseless, but pause-less. And the idea here is that in terms of the latency profile, you don't see any changes from the way that this works, regardless of certain things. So the heap size, we can go all the way from 512 megabytes to 8 terabytes without seeing any increase in latency. Allocation rate doesn't make any difference. How long you run it for doesn't make any difference. How much fragmentation, load profile doesn't make any difference to how the collector works. How can we prove that this works? Well, what we've done is we've developed this little thing called JHiccup. And JHiccup is all about measuring the latency of the JVM. So not your application latency in terms of what it's doing, how long it takes you to process transactions. How long does the JVM take to do certain things? We put a thread alongside your application, doesn't interact with it. All it does is spend most of its time asleep. So it goes to sleep for 1 millisecond. When it wakes up, it looks at the system clock and says, I expected to wake up 1 millisecond later. What time did I actually wake up? If there was a 20 millisecond garbage collection pause, you wake up 20 milliseconds later, and we record that delta, and then we can produce some graphs to show how well that works. Here's an example. So this is Elasticsearch running on 128 gigabyte heap, reasonable size. On the left is hotspot, on the right is Zing. So the spikes in the graph are the latency. And if we look at the hotspot, what we're seeing is lots of small spikes. That's minor GC pauses, collection of the young generation, and a couple of bigger spikes, which are major GC pauses where work is going on the old generation. If we look at the Zing side of things, it looks all very random, and there's some quite big spikes there, and it doesn't look very impressive compared to the hotspot version. But I've been deliberately misleading here because I've changed the scale of the graph to sort of highlight this. So on the left-hand side, hotspot is 0 to 8 seconds, meaning most of our minor GC pauses are around half a second, and major GC pauses are about 5.5, 6.5 seconds. On the right, with Zing, that's 0 to 80 milliseconds. And so if I set the scale of the graph to be the same, suddenly we see the real impact of Zing. So we've essentially eliminated all of the garbage collection pauses that we would have seen in hotspot. So now Elasticsearch is not seeing any latency associated with GC. Now, one of the things that people often say then is, okay, well, we're doing all the garbage collection at the same time as our application threads. Doesn't that reduce the overall throughput of the application? And the answer is yes, because the work of the garbage collector has to go somewhere. So what we did was we figured, okay, how can we eliminate as much as possible that side of things? So we basically said, okay, let's look at how the JIT compiler works. And in hotspot, you have this thing called C2, which is the JIT compiler that generates the most optimal performant code. We decided to replace that. Again, we didn't start from scratch. We looked around and found that there's this really good open source project called LLVM, which is essentially a sort of static compiler project for generating heavily optimized code. What we did was we integrated that with the JVM. So that was quite a lot of work to get it to work, rather than being a static compiler, to work as a JIT compiler. And we contributed that work back to the project as well. So it replaces C2 in the virtual machine. What this allows us to do is get better performing code out of the JIT compiler. So we can, in effect, eliminate the problem of that throughput reduction because we're doing garbage collection concurrently by having better performing code for the application side of things. What we can do is more what are called speculative optimizations. We can make much better use of things like vector operations that are very common, single instruction, multiple data type things. We can do better intrinsics, more inlining of code and things like that. So we actually get really significant performance improvements by doing this. Last thing to talk about is, as I said, this idea of warm-up. And if we look at the sort of speed of an application, because we're seeing a gradual move from interpreted mode through the C1 compiled code, C2 compiled code, de-optimizations, re-optimizations, and so on, we get an application warm-up time. And we get that every time we run an application, which is what we don't want to have. So what we've done is to create a thing called Ready Now. And the idea here is that we let the application warm up, get to a point where we're happy with the performance, and then we save a profile. And the profile consists of 4 things: all the classes that are currently loaded, all the classes currently initialized, all of the profiling data that was collected by the JVM as the C1 compiled code was running, and that was fed into the Falcon JIT compiler to provide optimized code. And very importantly, speculative optimizations which failed, where we had to throw away our compiled code and then recompile it. So we don't want to have to go through that again. So we take that profile whenever we want, and then the next time we run the application, before we get to the main entry point of the application, we will load all of the classes that we can, we'll initialize all the classes we can, and then we'll pass all the methods to the compiler to get it to compile based on the profiling data and based on the speculative optimizations, which we don't want to fail. So that means that by the time we get to the main entry point, we're running at about 98% of the speed that the code was running at when we took our profile. A couple of transactions when we start running main, and we'll be at 100%. To make that even better, what we've done is to introduce another thing most recently called compile stashing. And now what we do is, in addition to including those 4 things that we had, we also take a copy of all the code that was compiled and generated by the JVM, by the JIT compiler. Because we know that the Falcon JIT compiler is fully deterministic, if we've got the same set of inputs in the form of the method that we want to compile, plus the profiling information and various other bits and pieces, then we know that we'll get exactly the same compile code out of the other side. What that allows us to do is to avoid having to do a lot of the compilation work before we get to our main entry point, because we already have that code from the previous run, and therefore we can just reuse that without having to generate new code, which will be the same. So what that does is it helps us to eliminate a small problem that we had seen with the idea of ready now. So ready now has a much steeper graph in terms of the warm-up, so we eliminate a lot of that problem. But there was a lot of work that was going on before we could actually get your application code running. With compile stashing, we reduced that time by up to 80% and reduced the CPU load by up to 80%, so by up to 60%, sorry. And so now what we've got is really almost the ideal performance graph. So if I just kind of summarize that, if we look at the way that these things work, by using C4, what we're doing is eliminating the garbage collection pauses once our application is up and running and doing all the work we want it to. By using Falcon, we can actually get better performing code. So we raise the level, and that accounts for the fact that the garbage collector is running concurrently and so might reduce throughput. And then ready now and compile stashing is all about moving that envelope out, so we eliminate as much as possible the warm-up time associated with the application code running on top of the JVM. So that is a very brief kind of discussion of Zing JVM. The idea is to start fast, go faster, and stay fast. And what we're really looking for is consistent latency and consistent throughput. And that's really what's required for the kind of situations that we're going to hear about in the next few slides. Very simple replacement for other JVMs. You don't have to recode, you don't have to recompile. And if you're interested in trying this out, go to azul.com/Zing trial, and you can try it free for 30 days. And we'll help you with that. We'll even help you generate some nice graphs that you can show to your boss. So with that, I'm going to stop sharing my screen and let Denis take over. There we go.
All right. Yep. Give me a second.
Hopefully I haven't taken too much time.
Folks, no. Just you're a role model for how to stay fit in time, not to go beyond the allocated time slot. So I will try to carry on. Okay, so where's the share screen? And by the way, guys, while I'm switching the screens, don't hesitate putting your questions in the chat window while we have Simon in here. All right, here is my screen. And I need to share it. Okay.
Yes.
Present from here. All right, good. I hope that everybody can see my screen. So we will start. So right now, we need to review the second component of our low latency system based on Java, and that will be Apache Ignite. I'm just curious, guys, if anybody doesn't need any introduction to Ignite, just put a +1 or thumb up icon in the chat window. I'm just curious to see how many of us are already using Apache Ignite. But anyway, for the rest of the guys, let's do this. It's sort of speed dating to Ignite. First of all, Apache Ignite is a memory computing platform. But don't be puzzled by this slide. It might look a little bit complicated, but I would recommend you thinking about two primary components when it comes to Ignite. The first one is Ignite has a distributed multi-tier storage. And the second primary component is a variety of APIs that are well integrated with this distributed system. When it comes to the distributed multi-tier storage, by definition, as a in-memory computing platform, Ignite is capable of keeping and storing and processing all your records from memory, but that's not all. Also, Ignite can persist all your records on disk. And here you have two options. You can use your external database, like a relational one, or you can use Ignite native persistence. On the following slide, I will explain you why, when, and why you would select one of the options. And on top of this multi-tier distributed storage, Ignite provides like SQL, key value, map reduce APIs, transactions, and so on and so forth. When we are talking about Ignite primary use cases, so that you can better understand how this product and project is being used, first of all, you can use Ignite as a classic cache, as a distributed memory cache that boosts performance of your applications or resolves, eliminates bottlenecks of your backend systems that are powered by, let's say, relational databases. And here is Ignite as a cache. You can use SQL, you can still run transactions over this cache. And also this cache, Ignite as a cache, supports so-called write-through synchronization model. It means that whenever any record gets updated in Ignite, Ignite can kind of send this record down to your database automatically. The other use case of Ignite is Ignite as a in-memory database. And in this case, nothing changes from the API standpoint, but the only change is how Ignite persists your records. And here is we're using Ignite native persistence, not a third-party database, but our own component. And the difference here is that once you enable that persistence option, you first no longer obliged to keep and cache all the records in memory. You can cache as much as you can afford, as much as memory space you have. And also, as a result, you're getting so-called instantaneous restarts of your cluster. If your cluster went down, and when you restart it, you don't need to wait while, let's say, terabytes of data gets preloaded back in memory. It's a really time-consuming operation. And Ignite, once your cluster is up and running, Ignite can serve all the records from this. So that's the primary difference between those two persistence options. And the other use case that is being used widely by many enterprise companies is Ignite is so-called as a shared in-memory data store as part of your so-called digital integration hub architecture. This digital integration hub term is being coined by the analysts, but I'm okay with it, I like it. And the idea here is simple. Let's say usually you might have many databases, disjointed databases that store various data sets. And here is Ignite is represented as a shared distributed storage that, let's say, keeps a subset of the data from your database A, a subset of the data from the database B, and then all your application or some applications and some services can go to Ignite directly and use all those now available data sets from memory, and they don't need to go to those various databases. That's how Ignite is used. And next thing is that when we are preparing to this talk, to this session, generally, we were doing a lot of internal benchmarks. Like we were using special benchmarking tools, benchmarking tests that are in a toolbox of well-known banks. And how this benchmark looks like. Generally, we studied 3 nodes Apache Ignite cluster. Every Ignite cluster node was running on Azul Zing Java virtual machine. And then we had a classical application connected to this cluster. So that cluster was provisioned on AWS. Every cluster node was given 6x large machine. Cluster-wide, we've got 72 cores, and overall we had 600 gigabytes of RAM and 45 terabytes of disk. And what we were testing? We were comparing Azul Zing, C4, and all those other features of Azul Zing with Hotspot G1 garbage collector. When we were talking about Apache Ignite cluster configuration, for the very first test runs, we were keeping all the data in memory as well as on disk. The full copy was available in both tiers. While with the second use case, we decided to challenge the current configuration of our cluster and load 3 times more data, like 600 gigabytes. But we decided not to, to scale out our cluster. We decided to replicate the story of the Southwest airline that Simon told you at the very beginning, when Southwest had to sell one of their jets, but still by reducing that turnaround latency time, they were able to operate on the same number of routes, and they were able to stay in business. And here is we were trying to see, like, right, we already have our cluster, and that cluster kind of can provide us with all the required throughput and latency options. So, like, let's try to use most of it. Let's triple the data size and see how well it will perform before we scale out it. And how the benchmarking workload looks like. Actually, as I said, that's a real benchmark that is being regularly executed by one of the biggest banks. And what happens here, like we are going to compare distributed transactional reads. So the rate is 1,000 reads per second, and the target latency is 15 milliseconds for 4/9 percentile. At the same time, in parallel, we will be running distributed transactional updates. Here is we have to the requirement is 2,000 operations per second, but the latency is not that harsh. We should stay within the boundary of 50 milliseconds for 9th percentile. And as Simon has already presented you to the G-Hiccup tool, that was the tool that helped us to measure the latency time of the virtual machine. So let's check the very first benchmarking results. That's for the case when we loaded our 3 nodes Apache Ignite cluster with Azul Zing Java virtual machine. Just we loaded 200 gigabytes, and we stored this data both on memory and on disk. So for transactional reads, that's the first graph. To the left of the screen, you have their numbers for J1 hotspot. To the right, we have Azul C4. So here, as you can see, like that, the graphs looks pretty similar, but there is one trick. I'm cheating you because if you pay attention to the scale of the graphs is not aligned. So if we equalize the scale, you will see that in fact, Azul C4, we did not notice any kind of significant pauses. Our whole system was able to operate throughout this benchmarks execution time. We were running it for 2 hours, and everything went fine. As for the hotspot, unfortunately, we were not able to stay within the 15 millisecond latency for the 4/9 percentile, and that's what happened. So unfortunately, so when it comes to the transactional updates, so here is I need to clarify that when it comes to the reads, all the data were being served from memory. So we will not give into this because Ignite had a copy of every record in your primary memory space. But when it comes to the updates, in this case, Ignite was for every operation, like for all those thousands of transactional updates, it was updating both in memory copy and the copy on disk. And in this case, the graphs look like this way. Again, if we equalize the scale and remind ourselves that the target latency was and is 50 milliseconds, that's how the graph looks like. With Azul Zing, the profile is ideal. Unfortunately, with hotspot, it was kind of, again, impossible to achieve the required latency for the 4/9 percentile, not only for 4/9 percentile, but also for 3/9 percentile. So right now, let's talk about internals of Apache Ignite. I don't want to spend too much of your time, but I also want you to understand how this system, how the storage system is designed. As a Java middleware, right, we still use Java heap, but at the same time, Ignite has its own off-heap memory space. So actually, that's the space, that's a like several continuous data regions. So like whenever you start your Apache Ignite cluster node, that cluster node will request that memory space from your operating system. And that will be the place where your application records will reside. However, as a Java middleware, like as a Java application, Ignite will be using Java heap. We will be keeping there all the objects that are generated while your application code interacts with this cluster node. And if you can imagine, for the low latency use cases like this one, payments benchmark, the allocation rate is extremely high. It's like we are running thousands of reads per second, and we are running 2,000 of writes per second. That's why the Java heap will be stressed out a lot. And that's like the representation of the memory architecture on an individual cluster node. But whenever we are talking about the cluster, you just basically have a distributed solution. You need to have 3 nodes cluster, you just start 2 more nodes, and that's how you're getting a distributed like memory space and disk space if you need. When it comes to the native persistence, that's actually the one that we are using for this cluster configuration. Ignite was used as a memory, like as a database with its own persistence here. This one, I don't want to spend that much time here, but generally keep in mind that this persistence is not that different from, let's say, the way how relational databases keep our records on disk. Like we have write-ahead log files, that's an append-only file structure. Whenever any update arrives to your Ignite cluster node, it will write all this update to your write-ahead log, and then it will be able to carry on, the application will be able to carry on with the rest of the application logic. But then throughout, in some, sooner or later, Ignite will kick in so-called checkpointing process, and the checkpointing process will flush all the dirty pages, like those pages that were updated in memory, and they will be flushed to persistence file on disk. And once this operation, once a checkpointing cycle completes, we will be able to trim the size of our write-ahead log files. So that's actually how Ignite works here. But here is probably I will give you, as long as I still have a bit more time than expected, I can give you an interesting story how this whole persistence feature appeared in Ignite. Originally, right now, you can use it like, right now, as I said, it gives you two capabilities. First one, you don't need to cache all the records in memory. Let's say you always will keep 100% of the data on disk and then as much as you can in memory. And that allows you, let's say, to keep on disk much more data than can fit in memory. That's one feature. But the other capability, and that was the main driver for this feature development, is so-called fast or instantaneous restarts. Another customer like of GridGain and Apache Ignite user, when they were switching to Apache Ignite, they had one requirement. Their banking system, if it goes down, it must be recovered and become fully operational in no later than 3 minutes. They're given 3 minutes to restart the system. And the problem was that they were planning to store 3 terabytes, like 1 petabyte of data in Ignite. And that was impossible for them. Like even if they restart the cluster in 30 seconds, like in 1 minute, there is no way it was possible for them to preload 1 terabyte of data from disk in memory to Ignite. And that was the primary driver of that feature development. So first of all, we developed it, but when we were developing it, we decided, like, why not, guys? So like, let's use it like as a full-fledged persistence tier, so that our application code can read data from disk if any record is not available in memory. And right now, let's see how that persistence can help us. Let's say if we are running out of memory space, like let's simulate this scenario that I have enough disk, my disk is fast, and I just probably want to reduce some costs by keeping less data in cache. And so right now we are tripling the data size. We are going to load 600 gigabytes of data, but we are not scaling out our cluster. So these are how the graphs will look like. Again, to the left we have G1, to the right we have Azul C4. Again, if we equalize the scale, that's what we are getting. So with hotspot, we are not able, to meet the target latency even for 3/9 percentile, while with Azul C4 we are fine. But here, as you can see, that for 100% of the operations, we slightly violated this latency, but we were always in a good shape for the 4/9 percentile, and that was the target requirement. And next, when it comes to the transactional updates, again, let's equalize the scale. So far, so good, like not that many changes. So what's the summary of the story? The summary is that even if you are dealing with a memory computing system, depending on the technology that you select, you might not need to keep all the data in memory. And that gives you an ability to select like what would be your trade-off, performance versus cost. If you put all the data in memory, for sure, you will get the fastest and the best performance and latency. But also, it might be totally okay just to start a cluster of a certain configuration and let's say cache only a subset of the data in memory. And that's what we confirmed with this second test run. Also, what's important to note, like how Ignite keeps the data, because even for that benchmark or for any other use cases, Ignite is a distributed system, and whenever you keep your records, there might be some relation between the records. So let's say that we have two tables in Ignite. The first one is accounts table, and it might happen then the first node will keep Simon's bank account, while my bank account will reside on the other node. And there will be another table like transactions. And Ignite goes with so-called affinity collocation concept, like feature, that allows us to keep all the related records together on the same cluster machine. So here is all the transactions that belong to Simon are kept together on the same cluster machine, and that's good for us from the performance standpoint of view. And the same is true about my transactions. Why would you use it? Usually, whenever you run SQL queries with joins and you want to join data of accounts and transactions table, it would be much better if your records are collocated, because when this join happens on these cluster nodes, all the data that is needed for the join will be available locally. So you will be eliminating data shuffling over the network, and that way you will kind of reduce that network impact on your latency and performance. And also what we used for that benchmark, and that's what other Apache Ignite users use heavily, is compute APIs. Think of compute APIs as of your MapReduce framework that is available in Ignite. Those of you who work with Hadoop, like Spark, etc., you know, like the whole idea of MapReduce framework is just to create some application logic like Java task and schedule this logic for the execution in the cluster. And the same concept is available in Ignite. It's not that different. You just create your custom task, you send this task for the execution, and gets executed on the cluster nodes, and then if needed, those nodes can return you result sets, and you can reduce them. And here is I can tell you another story, and again from the banking sector. But so today I'm telling the stories from of financial organizations who use Ignite. But generally speaking, don't think that Ignite is used only by banks. Ignite is used all over the place across the industries. So that story is as following. So like some other bank, they usually have to execute one regular operation. They store millions of savings accounts in their system, and once a month they need to iterate through all those savings accounts, do some calculations, and apply an interest rate. And before they migrated to an Apache Ignite based solution, they kept and stored all the records in Oracle. And as with Oracle, that was a pretty powerful database and running on their expensive hardware. They would run a special application once a month, late night, when the load on the system was minimal. And that application would connect to the database, would bring all those millions records over the network to the application, would do all the calculations, would apply the final interest rate, and then kind of flash back all the changes to Oracle. It was taking them around 2 hours to complete the operation. It's not because Oracle is slow or Oracle is fast, right? We know that. The problem was that they had to move all the records like in batches or one by one over the network, but network is slow. And when they switched to Apache Ignite, like with the very first solution, again, also that was a memory cluster, distributed, all the data is in memory, but they kind of continued using SQL queries and the same approach. So literally they were moving data from Ignite cluster to the application, etc. And they kind of, in that case, they reduced the execution time of that procedure, but not tremendously. It was taking them 1 hour to do this with Ignite, like 1 hour and 30 minutes, not that different. But then we decided, to take and rewrite this logic in such a way that instead of putting data from the Ignite cluster, they wrapped this whole calculation logic in the Java compute tasks. And now they started sending compute tasks to the cluster. And once this happened, this all heavyweight and kind of compute intensive logic was running on the cluster nodes, and no any data was being moved off the network. And once they did this, this whole procedure began to complete in 15 minutes. 15 minutes versus 2 hours. And that's like the difference of what you can achieve if you can eliminate network usage, if you can eliminate data shuffling. So why network is much like, that's because all about physics. Let me go back. what this table shows you guys. In the first column, we have some of the basic system events that need to be executed by our CPUs. And the second column, we have actual latency. So how much time actually it takes for our CPUs to complete an operation to the left. But also all those nanoseconds, microseconds, and milliseconds, we do know that those are extremely small units, but we cannot as humans comprehend them. That's why the author of this table came up with the third column. It's like computer latency at a human scale, this latency in our universe. And basically how this calculation happens, like the author assumed that 4 nanoseconds are equal to 1 second, and then he translated the other latencies from the middle column to the other one. And here, as you can see that, yes, main memory access is much faster than disk access. It's like the difference between minutes or days or month, but network is much slower than disk, which means that even if you start like the most advanced in memory cluster, let it be Ignite or anything else, but still your application logic will be triggering a lot of data shuffling over the network. You can kind of kill all the benefits of your in-memory system, because like the data will be shuffled over the network. And this example of procedure that we're applying the interest rate for the savings account is an interesting story to keep in mind. So like keep in mind, if you're building something in memory, take care about the minimal usage of your network so that your application kind of doesn't stress out your network. And here is like the final couple of slides. Let me show you another system. I was in the beginning, I was saying that when we are talking about payments processing, that's a multi-step process. That benchmark that we showed you actually is one of the steps of that system. So when you basically need to kind of accept the payments, you basically need to read the current balances, and you need to adjust those balances because someone is buying something and someone is selling something. But there is another step that is in this payment processing, which is transaction fraud detection. So, and how it's being done with mainframes. Usually mainframes are powerful machines running like IBM Z's. And whenever this transaction approval request arrives to that mainframe, the mainframe can extremely fast kind of open transactions history of my bank account or Simon's account, and then Starbucks transaction history, and quickly validate and check if my transaction is fraudulent or not, and if this payment is allowed or should be rejected. With distributed system, if you're building this with distributed system, your architecture will be looking as follows. So again, you keep in mind like that affinity collocation, when we can keep all the related records together, and compute API. So how do we use affinity collocation and compute API, so MapReduce. So first of all the related records, like my transactions history or Simon's transaction history, it will be located on the same cluster machines. And that's good, because as soon as this payment verification would arrive to any of these cluster nodes, all the data would be available locally. At least I'm buying a cup of coffee at Starbucks. This request, let's say, arrives to the node 2, and this node starts the calculation. All my transaction history is here, and the verification procedures will kind of open. They will check my like 1,000 latest payments. And when it comes to the merchants history, like Starbucks, the thing is a little bit more complicated, because usually you will not be able to keep, let's say, the whole history of Starbucks on the same cluster machine. Otherwise, what here is you can do another trick. You can also split this history in chunks and put those chunks into separate machines. And then whenever you're going to do the fraud detection, you're just running your MapReduce compute tasks. Your Java task can arrive to the first node to verify that my payment that I'm doing right now at Starbucks is eligible. And then this node that received the very first call will see that there is a second chunk of Starbucks history that is stored on the other node, and it will go to this node and also will ask to run calculate some of the fraud detection variables on that node. And all that stuff will be executed in parallel. So that's basically how you design a distributed system, let's say, for transactions verifications if you need. because generally, and that's why you need affinity collocation. That's why you need to compute code, because with distributed system you want to eliminate network impact. So summary, like for low latency system, generally speaking, if you need a pos-less garbage collector, and that's what we likely confirmed when we were using Azul Zing together with Apache Ignite and GridGain, that's actually what you need. We've got those predictable and consistent latencies. Unfortunately, you know, like before we considered Azul Zing, we used and Ignite for some of the use cases, for some other use cases in banking systems, like again also for payments processing. And that time we had a lot of trouble because we were running on hotspot. The problem was that sometimes hotspot was able to show latencies, like good latencies, but they were not consistent. The thing would fire off, let's say, in 2 hours, like 3 hours, like after an application is running. And also the other requirements, if you need like low latency performance or scalability, look for things like Apache Ignite. I'm talking about Apache Ignite because I'm representing this community, I'm contributing to this project, but also there might be something else you can select. But the point here is that if you're designing this system, make it scalable. And if it's possible, keep your data in memory, because memory is extremely fast storage there. And finally, how and where you can learn more, just a couple of references. If you want to learn more about Azul, Zing, and all those technologies like Ready Now, Falcon that were introduced by Simon, go to this page. And as for the Apache Ignite, just go to our main website, and that's where you can get most of your questions answered. So having said that, thanks, folks, and let's see if you have any questions.
Yes, Denis, we definitely have a lot of questions in the chat.
Okay, let me open the chat window. All right, I think that Simon, do you want to take the very first questions? I see that someone was, or have you already answered those?
So I answered the questions on there, but what I'd suggest is, because there's a question about when to use Spark versus Ignite. So if you take that first, because obviously we're a little bit short on time, I guess.
When to use Spark and Apache Ignite? So here is, I think that I don't understand like where this question is coming from, because Spark also goes with, Spark is a streaming and compute engine. So, and here is where you can find similarity. But in general, Apache Ignite is more than a compute engine. What I've shown to you is Apache Ignite is, first of all, that's it's a memory computing platform that consists of distributed multi-tier storage. So Ignite has its own embedded storage. And all the APIs of Apache Ignite are integrated well into this storage. So whenever, like while we Spark always need to bring data from somewhere else. It can be a Hadoop cluster, it can be a relational database, it can be your flat files, or Spark also is used together with Ignite. You can use Ignite as a data source for your Spark. So to answer in short, Spark is a compute engine, while Apache Ignite is compute engine plus database. And for our APIs, all the data is available and served right from our memory. But it also means that you can use Ignite together with Spark, and people do this. And what's the difference between, all right, yep. I think that at least I explained it briefly. If you wanna get in more details, please, yeah, sure. Ask the other questions. How does Ignite take care of sudden failure of the nodes? Does it work in leader for lowers fashion along with replication? So, so here is Apache Ignite is, when we're talking about Apache Ignite, so whenever you start in your cluster nodes, you would usually have several copies of your data. Let's say, even in this benchmark that I demonstrated you, we had a primary copy of your data and we have a backup copy of your data. So every node of your cluster, let's say, it's both a primary and backup. If one node, the one node can store a primary copy of my record, but also the other node will keep a backup copy of my record, which means that if any of the nodes goes down, nothing usually happens, because most likely some other node in your cluster had a copy of my data in the cluster, and your application will be able to stay operational. So generally, you can think of it as a replication factor. The more copies of the data you have, the more cluster nodes you have, the lower are the chances that you will lose any data if any of the nodes goes down. And also here is to say that unlike in Hadoop, you don't have any notion of name node, etc. Every node in the cluster knows how the data is distributed, including your Java applications. Whenever your Java applications connects to the cluster and wants to send, let's say, a simple key value operation, trying to get a record from the cluster, it will know which node to connect to. So that's because the cluster internally distributes that partitions and data distribution map. So the other question by Rajesh, how is Ignite different, efficient from features with Oracle Coherence, Hazelcast commercial products? So here is, I will put it this way. Like Oracle Coherence, Hazelcast, and Ignite, all those three products can be used for the caching use case. You remember that at the very beginning, I showed you that like Ignite can be used as a cache. But when it comes to the database use case, like the one we presented you below, you will not be able to use Coherence or Hazelcast. Ignite supports this native persistence that allows us to cache a subset of the data in memory, and that enables those fast cluster restarts, meaning that if your cluster of Ignite needs to be restarted, you don't need to load any data in memory. Unfortunately, with Oracle Coherence and Hazelcast, you have to do that. So generally, as a summary, you can use like all the three products, like Ignite, Hazelcast, and Coherence are good for caching, and that's your preference, what you would decide to go for with. But when it's come to the in-memory database use case, when you need like this advanced native persistence, when you need SQL, or when you need built-in machine learning APIs, that's where you would probably go for with Apache Ignite. Does Ignite support running on Kubernetes platform? Yes, Apache Ignite is agnostic to your to your deployment environment. You can run it on bare metal, you can run it on virtual machines, you can run it inside of Kubernetes, etc. It's up to you. I guess that I've answered all my questions. Yep, thanks.
Okay.
Do we have any other questions? So please post them in the chat or unmute yourself and ask with voice. Okay, Denis, here is the question for you.
So how is Ignite persistence different from Akka persistence? Unfortunately, I'm not that familiar with Akka persistence. But you know, like Ignite persistence, it's not something you would use separately from Ignite. It's something that was developed precisely for the needs of Ignite and memory computing platform. You cannot just take it and use it like for something else. So and that's like Ignite persistence. If to put it simply, that's just it looks like, and its architecture and everything is quite similar to the way how disk tiers of relational databases separate, like write-ahead log files, checkpointing, etc., etc. That's just a disk tier of Apache Ignite cluster that you can enable.
So please notice that we have here Twitter accounts of our speakers, so you can follow them with the questions even after event if you mention them. And sure, we will share the video, and you can also ask under the video in comments. I think it will be tomorrow, your time.
Yeah, I'll share the video on the group once we've got it for everybody to go over, or if you need to share it with any of your colleagues or any people that might be interested in watching it, we can get that up. So no worries there. Thanks again, Simon and Denis, for taking your time. Really appreciate it. And yeah, hope to connect soon. You know, now a lot of these talks are virtual. Yeah, definitely keen to link up again next time you have maybe another topic you want to discuss. So yeah, please do stay in touch. And again, thanks for your time today.
Great. Thank you very much.
Thanks for inviting. Yeah, it was a pleasure.
Take care.